So the angle of deflection is increased by, obviously, current is one of the factors. Increasing the current, changing the polarity, no. Increasing the resistance, no. Increasing distance, so very simple question. So question 1A answer. Okay, question 2. Hi, Kaif. When is your trials? We try to do some questions today. Okay, so then before I continue with the electromagnetic induction. So question number 2. So just now we were looking at this question. So this is basically about the force experienced by a conductor which is placed in the magnetic field. Okay, so in what way we can actually increase the degree of deflection? So an example we have discussed in the last class. Okay, so one, we increase the magnitude of the current that's flowing through. Reduce what's that? Reduce the resistance. Okay, so of the wire R. Okay, so increase the distance between the pole. Reduce the distance between the pole. So then the magnetic field will be stronger. So the best answer is increasing the current. Okay, that was what we discussed. So question 2. The diagram shows the direction of the movement of the current, okay, carrying conductor that is placed between two magnets. So N is not, S is south. Okay, Utara, Selatan, U and S. No, it's confusing. Okay, so then you have the direction of the movement. Okay, so which magnetic field pattern is correct to show the situation? Think. Okay, Sharmila gave answer A. How about you, Kaif? Kaif, how about you? Answer. This is the catable field that we discussed last week. Okay. Both of y'all are trapped. The answer is not A. See properly. There's something, there's trick you. See properly. Yes. So the best choice of answer is Canada. You choose A, I know, correct. You saw the arrow. But look at the arrow at the bottom here. It goes in the opposite direction. No, the arrow, it depends on the polarity of the magnetic field. So the magnet not south. So it has to be moving from the left to right. It's not that top left to right and bottom will be right to left. Cannot. It has to be because the whole thing is north. So whether it's up or down, the magnetic field must be directed from the north to the south. And since I know the net force is acting downward, direction of the movement, the force is acting downward, I should have more magnetic field, the catapult main field, okay, so more field on top compared to the bottom. So that will produce a net force acting downward. So yes, A and C, you can see more lines above. So yes, it's going to produce a net force downward. But then this one is just trick you. Okay, so perhaps for the C, all are in the same direction. The B and D definitely is out already. Okay, it is out of the discussion because you already know the force is down mean I must have more P lines on top. Okay, so be careful. It can be a trap for you. Okay, so question number 3. Question 3. Which compass shows the correct direction of the magnetic field? Is easy one. Okay, check. Kaif, how are you? Sharmila, Denmark. Kaif, question 3, huh? Which compass shows the correct direction of the magnetic field? So if you look at the cell here, this is positive and this is negative. So current will flow this way, down. So now how do I find the direction of magnetic field? So you must use what rule? So you must use the right hand grip rule. So when you use the right hand grip rule, okay, yes. So right hand grip rule, the thumb will follow the direction of the current and the other 4 fingers should follow the direction of the magnetic field. So see which one indicating correctly between A, B, C and D. So magnetic field, we are expecting the magnetic field to be like this. So meaning if you use your right hand grip rule, the magnetic field should be in a direction of clockwise. So now can you tell me which of the compass appear to deflect to the compass shows the correct, it deflects in the correct direction of the magnetic field? Ah, answer should be A. See, this is supposed to be it's supposed to be bonus question. Okay, so make sure so I can see. Okay, so weaknesses notice here. Okay, now look at the next question. So I think I will do some revision question discussion. Maybe even though, okay, so some chapters which we have not done, okay, I may just go and do questions. Okay, just some revision. And I'm recording this session. So this session will be also shared. Later I will upload to YouTube and then I will share it. Okay, question number 4. Okay. B, the answer. Okay. I'm not getting answers from you. Diagram 4 shows a pattern of magnetic field produced by a current carrying conductor. So this is north, south. Magnetic field should be downward lah. Okay. And then this one is current is flowing into the page. So by using your right hand grip rule, magnetic field is current is flowing into. So pointing in, right hand grip rule. The other three fingers are, other four fingers are on the direction of clockwise. Okay, I suppose clockwise. So right hand grip rule. So meaning your magnetic field is going this way. Okay. So which diagram is correct when the conductor carrying a current is placed into the permanent magnetic field? So when this comes into it, so what will happen? Okay. So there will be overlap between the both magnetic field. Okay, so because of that, okay, so when current is flowing in, I can use your Fleming left hand rule. Okay, so current is flowing in. Okay, magnetic field is acting downward. So then I will notice the force has to be to the, so you bring in, okay, so you will notice that the when you use your Fleming left hand rule, okay, so Fleming left hand rule, you follow, okay, this is the conductor, okay, and draw a side view conductor. The current is basically flowing into the page. Magnetic field of the permanent magnet is acting downward. Okay, so do it lah. So the current is flowing in using your right hand using your Fleming right hand. Magnetic field is acting downward. So you can see your thumb will be pointing to the left. This is the direction of the movement of force. So therefore now you see which one will be the best answer. So now I make it bigger. Which one? So I'm expecting the force has to be to the left. So right, wrong, salah. Okay, so whichever it is acting to the right will be which diagram is correct when the conductor carrying a current is placed in the magnetic field? I see something like different here. Here it is a cross, but here is a dot. Oh, because here is a cross. Here is referring to a dot. Okay, so if dot means, then the current is flowing out. Okay, so current should be flowing out of the page. So then I need to use my Fleming left hand rule. My middle finger, which is the FBI current, should be pointing to me. Okay, my middle finger should be pointing to you. Magnetic field should be down. So then I can see the thumb will be pointing to the right. So in this case, okay, so it should be to the right. Okay, because it's a dot one. We are referring dot. That is the thing confusing. Okay, I don't know why they give you this diagram above. And then in the question, okay, it is a dot, not a cross. So it has to be to the right. Okay, the force has to be to the right. So I see which one is to the right. So obviously A and B is out. Okay, since it is to the right, I'm expecting magnetic field from up acting down, north, south, north, south, up. This one is the opposite direction. Magnetic field. So the best choice of answer, what Sharmila gave the answer, boy. I don't think so. It can be boy. There is a bit of confusion in the question. So whether the diagram is correctly, is it magnify and see? Oh yeah, it is cross, 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 cross. Because yeah, I can see now. When you enlarge, okay, it actually appeared to be a cross. Okay, okay. The cross means it has to be to the, yes, okay, it is supposed to be. Then the best choice of answer should be boy. Yeah, okay. So it is a cross. There's a diagram mistake. So it is a cross. So we know magnetic field should not south. Okay, so it is acting from the top to the bottom. Okay, and using the right and green rule. Okay, magnetic field is a clockwise. Okay, so fine. So answer should be boy. Okay now. Sorry for the confusion because I could not see. Okay, for me it looks like a dot. Okay. Kai, you have been a bit quiet. Can you understand? These are purely based on the part of we discussed about force experienced by a current carrying conductor placed in the magnetic field, which relates to the Fleming left-hand rule, okay, to find the direction of the force, and the right-hand grip rule to find the direction of the magnetic field induced around a straight conductor. Okay, so carries a current. Okay, yeah. Next question number 5. Jamila, so far I think Jamila, sure, okay. So Kai, hope you're getting it. 5. There is about 6 MCQ questions, I think. We will try 6 MCQ questions, then we will try, then we will do the some of the structure questions. Diagram 5 shows the pattern of magnetic field. Okay, the direction of the magnetic field is determined by using, this one is your reason. The direction of the magnetic field is determined by using. Okay, yes. Which one? Best choice of answer for 5. So Fleming right hand rule, Fleming left hand rule, left hand grip rule, right hand grip rule. Which one you can use? Okay, so to determine the direction of the magnetic field is determined by using. So it should be the right hand grip rule. Okay, so right hand grip rule we use. So for example, in this case, current is flowing into the page. So my thumb is pointing into, so the right hand, the other 4 fingers will be pointing clockwise direction. Okay, done. Next. So, I think we have total of 7 questions. Okay, then it goes to structure. Question number 6. Come on, come on. Okay, I have the first answer coming C. So, which pattern of magnetic field is correct when nickel is replaced with copper? Nickel replaced with copper. The direction will not change. It will still the same. So we are using the direct current. Okay, arrows throws. Sounds weird for me. Okay, so direct translation, arrows throws. Okay, so so here so depend on the okay, so which is the pattern which is so pattern will not change. Okay, so pattern will be nickel. Okay, so change with the copper. Copper is a better conductor. Better conductor means it will have higher current. Nickel more resistance. So resistance current will be lesser. So the magnetic field strength will be weaker. Okay, but it's not that much significant. So you can see for nickel you have 1, 2, 3, 4 lines. So for copper, I'm expecting to have more number of lines. Okay, so A is out because for A, it looks like there's a large gap. Okay, so it has to be in the gap has to be increasing. So C also no, because I can see there's a large gap, then suddenly it becomes close. That is already very far. So the magnetic field should be weaker. For B, it looks almost uniform. C, I can see there is more circle. So when I see more circle and then the space between it is also slightly increasing. That indicates the magnitude of the current have increased, the magnetic field strength have increased because copper is a better conductor than the nickel. So therefore, okay, so the best answer here will be Denmark. Okay, so I think okay, Sharmila gap, Denmark. Oh, that's Sharmila gap, Canada. Canada is for which one? For the earlier question. Is it Canada for the earlier question? What was the function of iron filling? Okay, where's the iron filling? Oh, so iron filling is actually how to see the magnetic field pattern. You are not able to see the magnetic field pattern. So in order to see the magnetic field pattern, we will spread some iron fillings. So the iron fillings will be attracted by the magnetic field that is induced around the conductor. So you can see the pattern. Okay. So otherwise you will not able to see the pattern. Did you all did any experiment? This is a very simple experiment can be done in the lab. No, you didn't do any experiment. Huh? So when you do the experiment, okay, so you may have, okay, wait, just give me a moment, a check. I can show you a video or not. So Kaif, okay or not Kaif? Are you following? Being very quiet. Wait, magnetic field. Okay, so I found a video. Okay, so I will share that. We'll see.
With the help of a magnet,
Can you
a
all
piece of
hear me
clear
now?
glass or plastic, and iron shavings, you can be on your way to helping students
Could you
better visualize the magnetic field
can you see
all
my
magnets
video?
create.
Can you
Begin by placing the clear plastic or glass over a magnet. In this case, I use the cover of an old takeout tray. Carefully shake the iron filings out over the magnet and clear cover. You'll notice that as you shake, the filings will
you see?
begin to arrange themselves.
Hi students, are you able to watch the video? Are you watching? Okay, so this is it. So you see, is just spreading the iron filling.
Almost magically across distinct
That's iron
lines.
filling. So you can
This
see
is
the
a
iron
result of
fillings
the
will
north and
arrange
south
according to the
poles of
magnetic
each
field
shavings
that is
arranging
induced
themselves
around
with the
the
magnetic
permanent
field.
magnet. So if you do that with
When
the
done shaking,
current
make sure
carrying
kids
conductor,
observe the pattern.
if you do that with the current carrying conductor, so when you spread the iron fillings around a conductor which carries a current, the same thing. So the iron fillings will arrange, okay, so according to the pattern that you saw just now, a circular pattern. So then you will see that pattern visible. It is visible. Otherwise, we are not able to see that the magnetic field is there, but then it is invisible to us. So you're not able to see. In order the magnetic field is visible to us, we need to use iron fillings. Okay, so that it will the iron fillings will be influenced by the magnetic field and they will arrange according to the pattern that is induced around them.
Pattern both overhead and from the side. From the side, they'll observe that the field is three-dimensional, meaning the magnetic field extends in all directions from the North Pole and wraps back around to the South Pole. Consider trying this activity with a horseshoe or ring magnet to see how the fields are different than the bars. With the help of this activity, students should come to recognize that all magnetic materials create a magnetic field. That includes Earth's core. A diagram like this can also be used to see how well students understand that North and South poles attract and vice versa. Ask your students, why does the imaginary bar magnet inside the Earth appear to be upside down? Want to learn more? Visit us online at the Burlington Science Center blog or Facebook page. Thanks for joining.
Okay. So let's back to the question. So in this case, the best choice of answer should be 10-1. Okay, the last MCQ question. Question number 7. Okay, try. Okay, noted, Kai. So your internet was that not stable? Okay, fine, fine. So try your best to follow with the lesson. Okay, so A. Diagram shows a coil wire in a magnetic field. Okay, so the rate of rotation of the coil increase when the current is increased. Vertical length of the is increased. Distance between the magnetic field is increased. Thickness of both magnets is increased. Obviously, okay, so the current increase is one of the factor. No, thickness of the magnet, no. Thickness of the magnet does not mean that the magnetic field is going to be stronger. No. Okay, so that does not identify. Okay, because the magnet can be thick, but then that didn't mean the magnetic field has to be stronger. Okay, so a stronger magnet means stronger magnet. Okay, not necessarily a stronger magnet. Okay, must be bigger in size. Okay, but what I'm looking at is the vertical length of a coil is increased. Vertical length, rate of rotation of the coil increase when vertical length. Oh, no point. That's why I was wondering. It's a bit tricky though. Okay. So vertical length, no. Okay, you can see because I can see here this coil is just the length of the magnet. So if the vertical length of the coil is increased, no point. If the magnet size is maximum here like this, if you increase the length of the coil more than the magnet, no point. Because whatever that is beyond the length of the magnet is useless. Only the part, the length which is within the magnetic field will have an effect on the magnitude of the force. So if it is longer than the magnet, no point. Okay, so therefore, yes, confirm best answer should be A. Okay, so okay, I just wanted to see. Okay, so we have discussed this. Okay, so force of a conductor. So we will discuss through this one question. Okay, and then okay, so we will able to move on to the next is electromagnetic induction. Okay, look at this question. So a diagram 2.1 shows a current carrying wire placed between two opposite poles of two magnet. Okay, the wire swings upwards. Okay, so first, name the rule used to determine the direction of the force. Oh, So it will be the left hand. On, continue. State one electrical appliances that uses the rule as A above. Oh, this one you have to go out of the box to think. Moto. Yeah, okay. So yes, in moto. Anything, okay. Continue next one. Moto, electrical moto, fan. Okay, so at diagram 2.1, draw the resultant magnetic field produced. Draw the resultant magnetic field produced. So when they say draw the resultant magnetic field, what they are asking? So first, current is flowing here, meaning it is flowing out of the page. Okay, so the magnetic field will be current flowing out of the page. So the magnetic field has to be something like this. And then top is north, bottom is south. So you are expecting the magnetic field is going to flow from the top to the bottom. So, okay, that's the direction of the magnetic field. Okay, fine. So now you can use your Fleming left-hand rule. Okay, so to identify the direction of the force. Current is flowing towards you, middle finger is pointing to your nose. Magnetic field is acting downward, not to the south. So I can see my force is to the right. Okay, force to the right. So if I already know my force is acting to the right, so then I can draw accordingly for the catable field. Lah. So the magnetic field, I'm expecting the magnetic field, okay, to be something like this. Okay. So this will be what the pattern you are expecting. So at diagram 2.1, draw a resultant magnetic field produced. Diagram 2.1, okay. Then diagram 2.2, A, B, C. Using the arrow, show the direction of resultant force at diagram 2.2. Oh, this oh, you draw in this diagram. Then at diagram 2.1, draw a resultant magnetic field. A resultant magnetic field will be the same direction as the direction of the force. Okay, so the direction of the resultant magnetic field will be the same as the direction of the force. Okay. Done. I think that's all. That's question. Okay. Can you see the question? Okay, so we'll look into this. This is the question B. Sorry, paper 2, question for section B, whereby you will have a section whereby we need to come with some comments to explain. Okay, so uh, on the apparatus or instruments that has been introduced. So first thing is you need to understand the question, okay, and the information that has been shared in the question. So you need to use that values to analyze further how to answer. So depending on the situation. So diagram 3 shows 3 electrical motors design X, Y, and Z used to build a small portable fan. Motor electric X and motor, electric motor X. So they come with the English and Malay and English okay, sometimes. Okay, so we have electric motor X, electric motor X, electric motor Y, and electric motor Z. Okay, what is the difference? Electric motor X, it has fan blades, semicircular shaped permanent magnet. So that's a good feature. So semicircular shaped permanent magnet, it is a good feature whereby magnetic field can be focused because it is like this. So mean the magnetic field is kind of like focused. So the coil will be somewhere in the center. So all the magnetic fields kind of like focus through the coil at the center. Okay, then number of turns, okay, 50. And the battery, okay, so you have a battery, okay, so okay, fine. Okay, then next, for the electric motor Y, okay, so you have the, then you have a rectangular shape, okay, the magnetic field is not focused. So number of turns is 10, so number of turns are less. So change in flux will be, the amount of magnetic field cut will be lesser. Okay, then battery of one only. Then electric motor Z. So you have the fan blades. So rectangular shape, permanent magnet, and number of the turns 50, number of turns of coil 50. Okay. So this one has both uh, number of turns of coil, number of turns of coil 50. Rectangular shape, not good. Fan blades. Okay. So this is the specification that is given. So still feel motor axis more reliable than, because all the features semicircular shape, fan blades, and 50 number of turns. Okay, so all is needed. So we come to the question. Anything doubt? Okay, so on the question, to clarify before you can start to plan. So you understand? Okay. Okay. So I will share, okay, this question thing later. Idea. So maybe if you want to snap picture also, you can snap. So you have X, Y, and Z. So look at this. So read and get an idea first. Based on the diagram, state the suitable characteristics of the electric motor to be used to rotate the fan blade with greater speed. Give reason for the suitability of your uh, of the characteristics. Okay, number of turns of the coil. Okay, so number of battery use, shape of the permanent magnet, and determine the most suitable design of an electric motor that can be used to rotate the fan blades with a greater speed. So you have your characteristics and reason. Let's see. Okay. You try to draft out first the answer. So this is 8 marks. Okay, students, you decide, give you some time. Okay, so to figure out. Okay, so you can, if you're done, you can, in fact, okay, so take a picture and share into the group also. Easier if it is difficult to type. Okay, so this is total 8 marks, I suppose. Yes, 8 marks. Could you please drop it? Okay, so and give me the answer. Put it very simple. What is the characteristic? Okay, and what is the reason? So you choose from the number of turn, number of battery used, and the shape of the permanent magnet, and then determine the most suitable. So final conclusion: the most suitable design of the electric motor that could be used to rotate the blade with a greater speed. Okay. Wow, so fast. Okay, so got the answer from Shamila. Higher number of turns of coil cause more magnetic field will be cut. Okay, so more number of batteries. Okay, increases the induced more number of battery, more number of battery increases induced current produced. I could not understand that. What's that? More number of battery increases induced current produced. So current produced. So yeah, yes, that's correct. More number of batteries increases the magnitude of the current. So when the magnitude of the current increases, yes, so that is going to influence lah. Okay. So okay, that's accepted. Okay. Then mm, the yes. So the semicircular magnet to produce a radial magnetic field. Yes. So more number of battery increases the current. Okay. Okay. Let's start. Okay. Conclusion is which one is suitable? X, Y, Z. So you have X, Y, Z. Which one is more suitable? X. Yes. Finish. 10 marks cover. Okay. So it will be like for each characteristic and also the reason you have 1 mark, 1 mark. So you have you have three. Three what? So you have here. So 1, 1, 1, 1, 1. Then final. Okay, so you have to final. You will provide the conclusion. Okay, so X. So because then you must give a reason now why. So X because it has the most number of turn, it has the greater number of turn with more batteries and semi circle shaped magnet. Okay, so okay, see, it's very simple. Don't get scared of looking at things. Okay, so when you what's that? Think wise. Okay, so when you think wise and uh, see the logic behind it. Okay, so you will be able to get the answers, even though okay, I mean you didn't really okay, so studied about that, but some logical okay, so thinking may help you to figure out the answer. Okay, so done with that. That's for the chapter. So next for the part 4.1. So now 4.2. Okay, so before we go to 4.2, so we just take a short 5 minutes break. So okay, so we take a 5 minutes break. So now 9:41. Okay, so perhaps by 9:46, come back lah. We will resume the class. Okay, let's continue with the electromagnetic induction. I hope you get some understanding of what we have discussed. So for magnetic field, as I mentioned earlier, it is a situation whereby force experienced by a conductor due to magnetic field that is induced around the conductor. Okay, so and when a conductor is placed in the magnetic field, there is can be due to the permanent magnet, or it can be due to the conductor which carries the current. Okay, there will be magnetic field induced around. Okay, so when it comes to electromagnetic induction, is we are using the magnetic field, okay, to produce the force. So there is no electricity here. So we don't use power supply. But in the magnetic field, we use power supply in order to cause a force. So for example, like motor rotates because of the electricity that we supply. But when it comes to electromagnetic induction, there is no electrical energy used. We only generate the electrical energy. For example, a simple example is hydroelectric. So hydroelectric, okay, we produce the electrical energy at the dam. So when the water falls on the turbine, that causes the turbine to be rotated. Okay, so and then that generates the electricity. And the turbine works based on the principle of electromagnetic induction. Okay, so we have discussed about this. I think we already gone this part. Okay, to see how when a conductor plays moved within the magnetic field, so we observe a, a current that is induced, and then we have also seen that if you change when you increase the rate at which the magnetic field is being cut, especially between A and B lah. Okay, when you move perpendicular to the magnetic field, then the magnetic field will be cut, EMF will be induced, current will be produced. But if you move within CD, which is parallel to the direction of the magnetic field, there will be no magnetic field being cut. Okay, so there will be no current induced. All this we have discussed. So last class you can see until 18. Okay, so that's what we have basically covered. So we understand that is either, okay, so we want to move the magnet or we want to move the solenoid, for example, in this case. So we look into the B, solenoid. Okay, I suppose you all know what is solenoid. Solenoid is a coil. Okay, so we have the coil of n number of turns. So a coil n number of turns. Okay, so a specific length. Okay, so that is what we understand as the solenoid. Okay, so apparatus, bar, magnet, solenoid, at least 400 turns and sensitive center zero galvanometer or digital multimeter. Okay, material. So connecting wires with crocodile teeth. So set up the arrangement of the apparatus as shown in figure. Okay, so observe the reading on the galvanometer. I did mention before galvanometer, you can see galvanometer, the reading 0 is at the center. So it can deflect to both sides. So the magnitude of the current induced can be measured. Okay, so on both directions. So if you use normal ammeter, it can only show in one direction. The other direction, it will go out of the scale. So holding the bar magnet stationary near the solenoid as shown in the figure 4.17, observe the reading of the galvanometer. Push the bar magnet, okay, so push the bar magnet into the solenoid, observe the deflection of the galvanometer pointer. Hold the bar magnet stationary. This is one condition situation. The second situation, you hold the bar magnet stationary, observe the reading. Third, pull the bar magnet out of the solenoid, observe the deflection. And the fourth one, hold the bar magnet stationary, move the solenoid towards and away. Okay, so then see, so complete the table. with a tick for the direction of the deflection of the galvanometer pointer. So when both are stationary, the deflection of the galvanometer will be 0. Correct. Okay, now moves into the solenoid. Okay, so bar magnet and the solenoid is stationary. Okay, so there is a relative move. The moment one moves, then there is already a relative movement. Okay, only when both are not moving, there is no relative movement. There will be no magnetic field will come. If at least one moving, okay, there is a relative movement between them, so magnetic field will be cut. So here the polarity, okay. Okay, so here you have this is your positive, so negative. This is my blue, so red. Okay, so I have the north pole here, south pole here. So if I'm moving the magnet in, it will try to oppose. So when it tries to, okay, it's a bit difficult to conclude whether this is probably observation when you do the experiment. Okay, so it's quite difficult to so when this is so magnetic field, okay, so will be coming out from the north. So at this end, this is the south. So if it is south, depending whether you are moving it in or moving it out. So if you are pushing the magnet in, for the first situation, move into. So when I move into, it will try to oppose. Oh, okay. In fact, okay, so I was not able to explain, I am not able to tell you now because we have not discussed about the laws that involve in deciding the direction of the current flow, which is the Lenz's law. So this one is just for the experimental purpose. Okay, so when you do the experiment, you just record the reading. Okay, but then since now we are not doing the experiment, okay, so I need to base on the Lenz's law, okay, to make the conclusion. So therefore, hold on this. Okay. After I explain that, I will come back because I'm not sure how far you all have understood the both electromagnetic induction laws, Faraday's law and also the Lenz's law. Okay, so this exercise, okay, so this one we have to hold until we can even you talk about this, okay, so but at least this one is okay. But then here we need to use the knowledge of the direction current induced that is going to take place. Not current induced, sorry, the direction of the force induced. Okay. So hold on, we will come back to this. We'll just continue further. Okay, so with the one example we discussed earlier. So when a piece of a copper wire is moved across the magnetic field, an electromotive force, EMF, is induced in the wire. We use the word induced, meaning it is kind of generated. Okay, so it's not like what's that? Got obtained from the power supply. So this phenomenon is known as the electromagnetic induction, meaning when the current is or the EMF is induced. If the wire is connected to form a complete circuit, so the deflection of the galvanometer pointer is observed as shown in figure 4.18. So this shows that induced current is produced. And electromotive force is also induced in the wire if the magnet is moved towards the stationary. So this is the same thing we discussed. When the conductor is placed, it is moved perpendicular to the direction of the magnetic field. So then it is going to cut the magnetic field. So there will be a change in the flux, EMF will be induced, current will be observed in the galvanometer. That is, if you look at the side here, magnetic field refers to the magnetic field line that passes through the surface. So, and this is the surface where the conductor is moving. So this is the conductor, moving conductor. And this is basically, when you move in this particular direction, this is the area that is going to swipe across the magnetic field. So the conductor that moves and cuts magnetic field lines can be said to cut magnetic flux. Okay, so in that case, okay, so direction of the motion of the magnetic field. Okay, so now if you be this is the direction motion of the wire. Okay, this is the direction of the motion of the wire. Now you want to find the direction of motion of the magnet. This one we make the conductor. This is magnet are stationary while conductor is moved. The bottom one is magnet is moved while the conductor is stationary. So either way, not a problem. Both also can, provided that not both are in stationary. Any one is moving, meaning there is a relative movement, okay, between them. Any one moving. So there will be a magnetic field lines cut. So current will be induced. Okay. So this is actually similar to what we discussed last class. Any questions here, students? Is there any questions related to this? You need to clarify before I move on. Okay. Kaif, are you okay? Can you follow, Kaif? Okay then. So, but if the conductor cuts at an angle of other than 90 degrees, can the magnetic field still be cut? Yes, can. Only angle it cannot cut the magnetic field is when it is parallel. Any other direction can, but then the magnetic field lines will be, which is cut, will be lesser. So the EMF induced will be lesser when it is moved at an angle. Okay, so 90 degrees will give you the maximum. When it cuts perpendicular to the magnetic field, it gives you the maximum. Smaller angle, it becomes lesser and lesser. And the moment the conductor is moving parallel to the magnetic field, then the magnetic field cut will be almost zero. So that will give you the minimum. Okay. Perhaps later when we come to questions, we can see the diagrams, examples, so I can explain, okay, in related to this. Okay, look at this. When a bar magnet is moved towards or away from a solenoid, the turns of the solenoid cuts the magnetic field line. Okay, see. This is a bar magnet. So the bar magnet has the magnetic field line. So this is the magnetic field line. Okay. So when you move that magnet, what happens? This coil is going to cut the magnetic field. When they cut the magnetic field, there is a change in the flux. So according to Faraday's law, the moment there is a magnetic field lines being cut, there is a change in the flux, EMF has to be induced. So there will be a EMF induced between the two ends. So if this is part of a complete circuit, just say if I connect a galvanometer here, then I will have electricity. Okay. So magnetic field lines are cut by the solenoid and EMF is induced. So the turns of the solenoid cuts the magnetic field lines, electromagnetic induction occurs and the EMF is induced across the solenoid. Figure 4.21 shows the end of the solenoid are connected to a galvanometer to form a complete circuit. So the induced electromotive force will produce an induced current in the circuit and the galvanometer pointer shows a deflection. Yes, as simple as that. Okay, you will be able to show this. Okay. So, but it has to be part of a complete circuit. So, in order for the EMF to be induced. See, now I will explain to you how to identify the direction of the induced current. Okay, so over here, we don't know where is the direction of the induced current. Okay, look at the bottom. The magnet is being moved. Okay, we are moving the magnet. If this is the north pole, this end also will be induced to a north pole. You must understand. This end also will be induced to north pole because only north and north will repel each other. So that is one of the law, okay, which is the Lenz's law. Lenz's law has stated that current, all follow, Lenz's law stated, okay, Lenz's law, L-E, Lenz's law stated current will be induced in the direction to oppose the change. Okay, what it means? Current is induced in the direction to oppose the change. What that means? So current will be induced, okay, to see, since I want to push the magnet in, so it will induce to a north pole so that it gains our activity. So we want to plug the magnet into the solenoid, but then the solenoid will try to push the magnet away. In order to push it away, this has to be a north pole. Do you understand? Can you follow, students? Okay, huh? Okay, so yeah, I repeat it. According to Lenz's law, it stated that current will be induced in the direction to oppose the change. Meaning, if a magnet is trying to enter into the solenoid will try to push the magnet out. It will try to oppose. If I'm trying to pull the magnet out of the solenoid, then the solenoid will try to attract the magnet. So meaning it is always try to oppose the change. You understand that, Sharmila? If I'm trying to push the magnet in, the solenoid will try to push it away. If I'm trying to pull the magnet out of the solenoid, then the solenoid will try to keep hold, attract the magnet. Okay. So, so now based on this diagram, If I'm trying to push it in, okay, so it will try to push it away. So this becomes north. If it is the north, what will be the direction of the magnetic field? Okay, so how do I find the direction of magnetic field? Again, we go to the right hand grip rule. So right hand grip rule, your thumb should be pointing to the north. Okay, your thumb, right hand grip rule. Huh? So your thumb should be pointing to the north. So if I put my hand here, all my other four fingers, okay, uh, four fingers, but then my thumb will be pointing like this. My four fingers are like this. This is my right hand grip rule. Okay. So now, just now we use current. Thumb will represent the current. So now thumb is representing the direction of the north pole. So my north is here. My south will be here. So the other four fingers will show the direction of the current. So the current in the coil should be following this way. Use your hand, right hand grip. Your thumb should be pointing towards your north pole on your right hand side of the coil. Okay, here. So therefore, the other end will be a south, and the other four fingers are showing the direction of the current. So now you follow and see the direction of the current. So the current comes down, okay, goes up, comes down. Okay. No, correct, correct. Okay, so the diagram they showed wrongly. So the current correct. So if it goes up here, okay, so it goes up, okay, it comes down. So this is the direction of current induced, correct. Only galvanometer deflects in the opposite direction. I don't know why. Okay, the galvanometer should be deflect on the direction where the current is flowing. Okay, so we will notice that the galvanometer will be deflected to the right. Okay, what will happen is, understand? Understand, students? Sharmila? Right? So this is when I'm trying to push the magnet in. Now I will try to pull the magnet out. Okay, I'll erase the thing. I want to pull the magnet out. See, when I want to pull the magnet out, like this, meaning this is not, I'm trying to separate them. But this will be induced to now, oops, okay. This will be induced now to a south pole because I'm trying to separate the magnet from the solenoid. But the solenoid will try to attract the magnet. So when this happens, this becomes south, this becomes north. So now I use your right hand grip again. My thumb should be pointing to the north. Then my other four fingers are showing the current in the opposite direction. Meaning, now up. Okay. So you notice that the current comes down here. So it will induce the opposite direction. So current goes in the opposite direction. Okay. So to oppose the change. So that's how you find. So if you're trying to push the magnet in, the coil will try to push the magnet out. So according to that, you find out what is the polarity. Then you use your right hand grip rule. Okay, so thumb will be pointing to the north. Then the other four fingers will show the direction of the magnetic field. So that's how you determine, okay, the direction of the current that is induced in the circuit. Okay. So activity 4.1 shows that the induced EMF is produced by the cutting of the magnetic field lines when the magnet and the conductor move towards or away from each other. Electromagnetic induction is the production of an induced EMF in a conductor when there is relative motion between the conductor and the magnetic field, or when the conductor is in a changing magnetic field. So it is what I mean by production of induced EMF. Okay, so when EMF is produced, when a conductor, okay, so there is a relative motion between the conductor and the magnet. Okay, or when the conductor is actually moving through a region or area where the magnetic field is also changing. So meaning it is moving from a weaker to a stronger magnetic field, or can be from a stronger to a weaker magnetic field. So in that case, there is a change in the number of magnetic field lines cut. Because if the number of field lines cut or rate of magnetic field line cut is same, okay, if it is same, then there will be no EMF induced. There must be a change in the magnetic field line being cut. There must be a rate in the magnetic field line cut. Then only you will have EMF induced. Same like they talk about acceleration. Only when there is a change in velocity, you will have acceleration. If the velocity remains constant, no acceleration. So the same thing here. So there must be a change in the number of field line or magnetic field line being cut. Then only you have a EMF induced. Okay. So if the magnetic field lines cut is the same, then no EMF will be induced. Okay. Any question? Perhaps I'm sure. Perhaps you may be tired of trying to understand it. Okay, but eventually that's it. So you will able to understand after you try to attempt few questions, and from that questions, okay, so you will know what is basically asked in the exam and what you are expecting, and by working it out, you will have a better understanding about how the principle works. Okay, so what do you say in the info gallery here? Relative motion between two objects in a motion that results in the objects becoming closer to each other or further away from each other, A and B. So relative motion occurs between the object A and B if object A is stationary. Okay, that one is, well, in order to have a relative movement, is either A move, B stationary, or B move, A stationary, or both A and B move. Okay, so yes, that's it. If both are not moving, then cannot. Okay, so no relative motion between A and B is when the both objects are stationary and both objects A and B move with the same speed. Yes, see, both are stationary and both are moved with the same speed. So when both are moving at the same speed, means there will be no overlapping taking place. So there will be no magnetic field line cut, no change in the flux, no EMF will be induced. That is according to the Faraday's law. Okay. So to study about this, we can do a simple experiment. Okay, so factors that affects the magnitude of the induced EMF. I can simply, okay, do a coil, okay, so around a insulated copper wire. Okay, So around a PVC pipe. Okay, so we must use the PVC plastic because we don't want the current to leak. Okay, so this one is when you say PVC pipe, okay, this is an insulator, so it will not allow the current to flow. So figure 4.22 shows an induced lamp made by a people. So he found that the LED light up with a different brightness when the magnet in the PVC pipe is shaken at different speed. So what are the factors that affect the magnitude of the induced EMF? See, this is actually uh, we can do it. Okay, we can just do. We can take a magnet. Okay, we can place the magnet inside here, and then both end you close with your finger, and then you try to like move it. Okay, so shake it. So when you shake, this is going to move left and right, and then outside there is a coil. So when it moves left, moves up and down, okay, so the magnetic field will be cut by the coils outside here. So that will cause the EMF to be induced in the wire, and then the LED will light up. A simple experiment can be done in the lab. Okay. So generally, okay, so it comes back to the observation just now. So this one is to study the factor that affects the magnetic field, uh, the magnetic field. So we can use two solenoid of a different number of turns, then we can analyze. So number of turn, as we discussed, number of turn as an effect. So when you increase the number of turns, the magnitude of the EMF induced for the same relative movement speed will increase depending on the ratio. Okay, so more turns. Okay, so you're expecting more change in the flux, greater EMF will be induced. Okay, so that was the experiment observation is about. Then we can see. Okay, so all this is when you do the experiment. Okay, so you get your data, and based on the data, we can make a conclusion. But then since we don't do the experiment, we only will look into the final conclusion. Okay, which you can make on the observation. So one for sure, okay, more number of turns will cause greater EMF to be induced. When you move faster, then there is a greater relative movement, the EMF induced will be also greater. Okay, so okay, so we will do a conclusion here. So just before, okay, so this is what we are talking about just now, Faraday's law. So the magnitude of the EMF induced if more magnetic field lines are cut in a certain period, okay, time. So Faraday's law has stated that the magnitude of the induced EMF is directly proportional to the rate of cutting of magnetic flux. Okay, the induced EMF is directly proportional to the rate of cutting of magnetic flux. Okay, so with this, I will stop here. So today is 26/10. 23. So we stop here. Next week, okay, we will be doing on the current direction of a current induced. So this is related to your Lenz law. Okay, so we will stop here. Thank you, students, and wish you all the best. Okay, so most of the school, the trials will be starting soon. Some have started, some is going to start tomorrow. So wish you all the best with your trials. Don't worry much. Do preparations as much you can. Okay, so and just go. Okay, do the exam. Get the feel of doing the exam. Try your best to a level best. Don't leave anything empty. Okay, you answer. Try to answer. Try to think simple and figure out for the answers to be included. Okay, don't think too complicated. So as I say, always I will say to my students, you must have a certain habit of reading a question. Okay, It's same like when you're talking to people. You must be talking, able to convince them, way to convince them. Language, your body language, your face appearance, your say. So when you read the patient, also you must have some technical ways of reading the patient so that you tackle the patient. So you will tackle the patient before the patient tackles you. I will say. So when you read, you need to understand, you need to underline, you need to take the key things. Okay, so the keywords. So all that will help you to tackle the patient. So then, fine. But the moment you read the question for the first time, then you don't know what is happening. You read for the second time. You have some idea. You read for the third time, meaning the question is already tackled you. So the more you read, the question tackles you. Okay, so you may get sometimes irritated, but it's okay to read one twice. But make sure you get a clear picture of the question. Sometimes when you read, our mind is already like beku. So your mind already saturated. So you're not able to think beyond, okay, to solve the problem. Then you jump to the next question. This all are reason I say is the question already tackled you. Okay. So yes, experience this. Learn. So with that, thank you, students. Okay, so all the best. Bye bye. See you all next week.